Good morning, Gen Chem 2. I love it. We're back. We are in the last little bit of our kinetics unit, and the plot thickens. This is awesome. This is the two videos we've been waiting for. We're going to get the most information out of all of our kinetics from that mechanism. And we started laying the foundations in our last video series for mechanism and our rate determining step. But we're going to learn even more. I love it because these next two videos, we're going to take this video to kind of define everything like we've done in the past. Let's line everything up. Let's define everything. And then we'll take our second video and we'll do some calculating. I love it. So this is so awesome. We just ended in learning that our kinetics can give us our reaction order. So let's make a little chart here. We can get to the order of our reaction. And then from that order of our reaction, we can get to ideas in a mechanism. So for example, we saw in our last video, what if we have two NO2s and they are needing to collide? So in other words, this was our slow step. And then that slow step was our rate determining step, and it was second order. All right, easy peasy, right? Can't we just take this one and this one, have a collision, and we form our product? Done. Not so fast. So it turns out that you can actually calculate this. And also, we've got a little cliffhanger. I'm just going to put it up here in the corner. We spent a lot of time talking about how concentration can change your rate, but we left two little ideas that were really important until the end. So let's bring those back. What about temperature? That affects rate, but we really haven't explained that yet. And what about a catalyst? Again, that doesn't actually, neither one of these do a darn thing to your concentration. So how do those actually affect rate? Well, we're going to tie all of that in with something called our collision model. Remember, anything past a second order reaction involves collisions of molecules. Okay, awesome. So what if you could just calculate those collisions? Well, it turns out you can. You can calculate something called a collision frequency. If you know your concentrations and you know relative speeds of molecules, which can all be calculated, you can literally calculate something called that collision frequency. This is a physical calculation. We're not going to calculate it, but we're going to use it in some equations. So this was done about 200 years ago, 150, 200 years ago. Let's calculate that collision frequency. Okay, well, that should match then your rate. Because if we just learned that we need two NO2s to smack into each other, and we can figure out how many collisions are happening in our reaction, well, that should give us our rate. Done. That would be so straightforward. You know, that's not at all how Mother Nature works. So it turns out in those initial experiments that collision frequency does not actually equal your rate. And this was actually studied by someone called Arrhenius, which we're going to see in Unit 4. Arrhenius is also our acids and bases definition, the original definition of acids and bases. So, we've got to figure out what else is happening there. Why aren't they equal? If we just figured out we need collisions, why aren't collisions always producing our product? So in other words, all of our collisions don't equal forming products. In fact, you have so many more collisions than products. You have many, many more collisions than products. Okay, why? So Arrhenius really came up with the first. And this is an awesome, we're going to have 2 qualifications on our collision frequency. And Arrhenius had an idea for the first. Okay, well, wait a second. Each one of those collisions has to have enough energy to make and break bonds, right? We just learned that in thermo. You have to literally have a number of kilojoules or kilocals, enough energy to actually break those bonds and make those bonds. So we need enough energy to make and break bonds. So that energy is going to come from those collisions. And he called this energy activation energy. It is energy, just like in our thermo, but what we're going to do is put a little A on it for activation energy. So in other words, your collisions have to have enough energy that they can actually overcome that barrier to break bonds. So our NO2s just smacking into each other wimpy, not enough energy to actually break bonds. You need to have enough energy to break those bonds. Okay, so then, all right, so let's consider, let's say just any bond. I happen to have a bromine nitrogen bond energy written down. So what if we're looking at a compound that has a bond like this? Well, we can read that from our bond energies table. What if you've got kilojoules? So you need to overcome this. You need to have a collision with enough force that it has that 243 kilojoules. And this is all going to come from kinetic energy. Aren't we hitting on something here? What is one major factor in our molecule's kinetic energy? Temperature. This is where temperature affects our actual rate and that rate constant. So it turns out that we need to keep in mind our temperature because that is going to affect that rate constant. Isn't that awesome? Okay, so what if we figure this out? Wait a second. Is anybody thinking what I'm thinking? Well, Dr. Morty, what does this do to our energy diagrams we learned in our thermo unit? Well, in our thermo unit, didn't we draw our energy diagrams like this? If it was some kind of reactant to some kind of product, if it was endothermic, or maybe we drew it the other way. If it was exothermic. So where do you put activation energy in there? Well, we need to actually change our energy diagrams. So what if we're starting with some reactants? We know we need to collide with enough energy to break bonds. And we're going to end up as an exothermic process. Over here, our products. But we literally have to overcome some kind of energy to break those bonds. So do you ever see energy diagrams with a little hump in there? This hump is our activation energy. So we are now, for the rest of the semester, going to change what an energy diagram looks like. We're going to include that activation energy. And then what is the actual bond energy and change in internal energy we've already looked at? That is this one. So that's where we're going to learn that this is exothermic. That's our enthalpy. So that is that change. So this little hump in here that we've got to overcome is our activation energy. So it would obviously be pretty cool if you could calculate that. Well, we can. So that's where this is headed. So there's actually, Arrhenius came up with an equation. Let's put that in. And that is that your number of collisions. Now this is our beginning place. This isn't the actual equation that we're going to calculate with. I'm going to give in just a second. I want to give the theory first. To our total number of collisions. Now we need to include that activation energy, and we have to keep in mind that temperature has a huge effect on this. And so it turns out that rates are exponentially affected by temperature. So this equation is E then to the activation energy. And then wait for it, this is so fun. We're going to put in the gas constant and temperature. So we're literally got to include temperature, and that is a huge factor in there. Why are we including the gas constant? Because an awful lot of these studies were done as gases. It's much easier to calculate those collisions as gases. And then here's our activation energy. So how do we turn this into something we can actually calculate? Well, there are two forms that we'll hit in our next video, but our real form that we can recognize from Arrhenius is that our rate constant, this is our rate constant. Our rate constant is going to govern how many productive collisions we have. Those productive collisions turn into products. That is coming from our rate constant. Okay, our A is that frequency factor, those collision frequencies. Let's call that a frequency factor. And then all of this is exponential to our activation energy. All right, so go ahead and put a box around this one. This is our Arrhenius equation. We're going to manipulate this in the next video, however, and make a linear plot. So let's just put a big sparkle star here. This is our place to start. Okay, now what's awesome about this equation is that it turns out, hold your seats, this is a cliffhanger. Okay, we've done some major work here. So now should our collisions with enough energy, so our collisions with enough energy to overcome those making and breaking bonds. So let's say we hit our number of collisions with all of that activation energy. Does that then equal our productive rate and we start equaling how many products that we're making? That would be awesome. Not yet. Okay, so there turns out there's actually one more factor after the Arrhenius equation. So factor number 2 is orientation. So not only do you have to have the right activation energy, you also have to have the right orientation. Now, what does that mean? That means, let's say we take that Br N bond again. Collisions from anywhere. So let's say I'm just going to smack into oxygen. I'm just making this up. A collision here at the wrong angle, or here, or maybe here, is not actually going to break that bond. It turns out the way that our molecules work, we're going to smack into an anti-bonding orbital, it's called. You don't need to know that for this test. We'll see that in organic chemistry, but it turns out you have to have the right angle. So let's say a collision from right here has the right angle to literally break this bond and pop those electrons off this way or this way. If we're smacking into here, we have to have the right angle. That is orientation. Okay, so you've got to have literally the correct angle. Those collisions cannot be from just any direction. Okay, wait for it. This is a cliffhanger. This is so fun. This, my friends, is how a catalyst works. More often than not. A lot of our biological catalysts, what they do is hold a substrate in a particular formation. And they have that particular angle that makes that much easier to actually get the right angle. So catalysts can generally really help this. In fact, in biological systems, that's typically what happens. I want to take a little bit to just show that on an energy diagram. So how do you actually show on an energy diagram? Let's go from our reactants to our products. Here's our activation energy. What do catalysts actually do then? Well, they don't jack with activation energy. They don't do anything with that. But what they do is help with orientation, and they make this process easier. So what a catalyst does is it lowers that activation energy barrier. So that process is a little bit easier. Okay, so a lot of enzymes, if you picture your, this is a really awesome protein or enzyme, it's going to hold your little reactive substrate right there in a certain orientation. And that's going to make this part easier. Okay, I love it. So remember, there's two factors in those collisions. Factor number one was our actual activation energy. Factor number two, orientation. So we've got two things to consider. In fact, I feel a list coming on, don't you? Let's write a little list here. So when we're thinking of that, our collisions and our collision model, we have activation energy, and we have orientation. Okay, highlight that. That's a big one. And then let's stop this video here, and then we're going to turn right around. Now that we've got both factors, we're going to turn right around and calculate it. Let's calculate that activation energy, and let's see how that really changes with temperature. It's going to be awesome.